85 miles of concrete tunnel, built in 1944, carry half of New York City's drinking water to 9 million people. For decades, engineers have watched it leak up to 35 million gallons a day, escaping into fractured bedrock beneath the Hudson Valley. In 2022, the city shut it down for the first time in its history. What inspectors found was, in some places, better than feared, and in others, far worse. But this aging tunnel is only one layer of a system most New Yorkers never think about. The New York City Department of Environmental Protection manages a sprawling network that delivers more than 1 billion gallons of drinking water every single day to 9 million residents and commuters. This massive gravity-fed system spans 19 reservoirs and 3 controlled lakes, drawing from a protected upstate watershed that extends more than 125 miles from the city. Because these mountain sources are heavily safeguarded, the water requires no filtration before distribution, making it one of the largest unfiltered municipal water systems in the world. Once the water reaches the city line, it is funneled into a subterranean grid of over 7,000 miles of water mains. This buried network is the silent engine of daily life, supplying the pressure necessary for high-rise apartments, hospital sanitation, and critical fire suppression across all 5 boroughs. Yet, the physical infrastructure supporting this daily miracle was largely built between the 1890s and the 1960s. Roughly 40% of these underground pipes were installed before 1941, with some cast iron mains dating back to the late 19th century. Operating a system of this vintage requires constant, high-stakes management. Many of these key distribution mains have remained in continuous service for over a century, carrying water under constant pressure without ever being shut down for internal inspection or structural repair. The city relies on an invisible foundation that has aged decades past its intended lifespan, quietly holding up the weight of a modern metropolis. At the heart of this vast network lies a single, concrete-lined conduit that dwarfs all other infrastructure in the system: the Delaware Aqueduct. Spanning 85 miles from the Catskill Mountains to the northern edge of the city, this subterranean giant remains the longest continuous tunnel ever constructed. Completed in April 1944, when Mayor Fiorello LaGuardia opened the emergency diversion gates during the height of the Second World War, the aqueduct has run continuously for more than 80 years. Today, it functions as the irreplaceable spine of New York's water supply, conveying between 500 million and 600 million gallons of water every single day. This single tunnel satisfies approximately half of the total daily water demand for nearly 10 million people, moving massive volumes of water entirely by gravity. But this critical conduit is structurally compromised. In 1990, a utility worker at a Hudson River power plant first discovered unexplained water losses, prompting a detailed investigation by municipal engineers. By 1992, the Department of Environmental Protection confirmed that the aqueduct's massive concrete lining was cracking under intense internal pressure, forcing clean water outward into the surrounding bedrock. Current engineering estimates put this constant leakage at between 15 million and 35 million gallons of water lost every single day. This is a volume of drinking water large enough to supply an entire small city, escaping silently through fractures hundreds of feet underground. Because the aqueduct must operate under continuous pressure to meet daily municipal needs, it cannot simply be shut down for standard inspection or repair. For decades, engineers have watched these fractures, knowing that half of New York City relies on a single, aging concrete tube that is slowly bleeding its contents into the earth. Without any immediate structural redundancy, this single line represents the ultimate vulnerability in the entire municipal system. 60 miles north of New York City, beneath the rural town of Wawasing in Ulster County, the compromised aqueduct runs directly through a zone of highly fractured bedrock. Here, the sheer hydrostatic pressure of the water inside the tunnel creates a self-propagating defect. Forced outward by this physical force, the water constantly scours and widens the natural fissures in the surrounding stone, traveling along underground faults until it reaches the surface. This continuous erosion has transformed a deep structural failure into a daily crisis for the local community. Homeowners watch yards gradually sink, asphalt roads crack, and residential basements flood with clean, pressurized water, even during dry spells. In private wells, drinking water frequently turns cloudy, contaminated with fine concrete and rock sediment pushed up from the tunnel hundreds of feet below. Sump pumps run constantly in affected homes to keep rising water tables from undermining residential foundations. Geologists and engineers studying the area in the late 1990s warned that this continuous washing away of subsoil was far more than a surface nuisance. Left unchecked, the steady migration of rock and sediment threatens to leave sections of the concrete conduit completely unsupported, risking a sudden localized collapse that would instantly cut off the flow to the city. In the early 2000s, municipal engineers recognized that patching the major leaks from the inside was impossible, while the aqueduct remained under intense operating pressure. The Department of Environmental Protection began planning a massive bypass tunnel to route water around the compromised sections beneath the Hudson River. Construction on this parallel conduit started in January 2013, beginning with the excavation of 350-foot vertical shafts. A 22-foot tunnel boring machine carved a 2.5-mile path through the solid bedrock, completing the excavation in 2021. The bypass tunnel alone cost $1.5 billion, representing the bulk of a broader $2 billion capital repair program. With the bypass built, the city prepared for the most precarious phase of the project, the connection. In 2022, the Delaware Aqueduct was shut down for the first time in its 80-year history, allowing inspectors to drain the line and conduct structural work. During this shutdown, the city operated with zero redundancy for half of its daily water supply. Water managers had to redirect every drop from alternate reservoirs, leaving no backup margin if another major pipeline failed. A single main break or pump failure during this period could have triggered widespread water pressure drops across the 5 boroughs. When robotic inspection platforms traveled through the unwatered tunnel, they revealed a highly complex structural picture. Some sections of the 80-year-old concrete lining looked remarkably intact, faring better than engineers had feared. However, other areas showed severe concrete delamination and fracture zones near the steel joints that were far worse than expected. These mixed findings proved that repairing the aqueduct is not a standard maintenance task, but a clear sign that the city's water system has crossed into a higher-risk phase of its operational life. At the city line, the water supply transitions from the massive aqueduct into a buried network of 6,800 miles of distribution mains. These underground channels range in size, from narrow 6-inch local pipes to massive 90-inch trunk lines, carrying water under high pressure directly beneath heavy metropolitan traffic. Much of this network is of a staggering age. The oldest active pipes beneath Manhattan were laid in the 1860s and 70s, designed to support a much smaller 19th century city of low rises and horse-drawn carriages. Today, these same cast-iron lines must survive the relentless vibrations of modern subways and heavy trucks. To maintain this massive grid, municipal crews replace roughly 70 miles of water mains each year. At this pace, it would take nearly a century to completely renew the entire network, leaving a vast backlog of aging iron buried in the earth. Because of this slow replacement cycle, the city constantly battles structural decay. Small, undetected fissures across the thousands of miles of pipe allow an estimated 36 million gallons of clean drinking water to seep into the surrounding soil every single day, a loss entirely separate from the aqueduct fractures. When these deteriorating pipes can no longer withstand the internal pressure, they rupture. The city now averages over 400 major water main breaks every year, proving that the infrastructure beneath the streets has its own severe vulnerabilities. In January 2023, a pressurized water main fractured beneath Fifth Avenue in Midtown Manhattan, sending a torrent of water onto the pavement and down into the transit tunnels below. The rushing water quickly flooded the active F&M subway lines, halting train service through a major metropolitan corridor. On the surface, the rapid erosion of the underlying soil carved out a sinkhole 20 feet wide, forcing municipal authorities to shut down several blocks of the avenue for 3 consecutive days. When emergency crews excavated the site, they exposed the source of the disruption: a fractured cast iron pipe installed in 1928. Having survived 95 years under constant pressure and the relentless vibrations of heavy vehicle traffic, the metal gave way. Resolving the crisis on this single block required a continuous engineering effort, resulting in an emergency repair bill of $2 million. While crews patched the street, the incident reveals what happens when hidden decay breaches the surface. A single dramatic failure along a world-famous corridor exposes the real-world cost of a system operating past its design life, showing how one broken pipe can instantly disrupt the daily routines of hundreds of thousands of people. A sudden, catastrophic failure of the Delaware Aqueduct would immediately cut off half of New York City's water supply, removing 600 million gallons of daily flow from the system. The remaining municipal network cannot compensate for a deficit of this scale. Within 12 to 24 hours, hydraulic pressure in the water mains would plunge by 20 to 30 pounds per square inch across Lower Manhattan and the outer boroughs. This pressure drop would quickly disable fire suppression systems in the city's tallest structures. High-rise buildings rely on municipal water mains to supply their Class 1 and Class 3 standpipe systems, which require a minimum pressure of 65 pounds per square inch at the highest floors to operate. Without this pressure, sprinkler networks become useless, leaving skyscrapers highly vulnerable to fire. Within 24 to 48 hours, the emergency would reach the healthcare system. Hospitals require immense continuous volumes of pressurized water to sterilize surgical equipment, maintain strict sanitation standards, and run cooling systems for life-saving machinery. Under emergency protocols, high-rise hospitals have a maximum of 48 hours to find alternative water sources before conditions become unsafe, forcing complex and dangerous patient evacuations across the region. If the aqueduct remains offline for multiple weeks, the public health crisis would trigger an economic collapse. Businesses, schools, and offices would be forced to close due to a total lack of sanitation. Major transit networks would face severe operational limits, and business continuity would fail. Financial analysts estimate that a multi-week water disruption of this scale would cost the city more than $100 billion. A single physical failure in this concrete conduit would rapidly compromise the basic safety, health, and economy of a modern metropolis. Preventing these disruptions is a financial challenge as much as an engineering one. The Department of Environmental Protection has identified $2.1 billion in urgent water infrastructure needs over the next decade. While federal grants are available, they require local matching funds from a municipal budget already strained by competing demands. To help fund these repairs, the city has increased municipal water rates by 80% over the past 10 years. Yet despite these rising rates, the maintenance backlog continues to grow faster than the repair rate. The city currently replaces about 70 miles of pipe annually, a pace that requires a century to cycle through the entire system. To begin reducing the backlog, city estimates show that crews would need to triple their current replacement rate. Addressing this deficit requires a mix of strategies, from faster pipe replacement and targeted acoustic monitoring to redundancy planning for major transit and hospital corridors. Stronger emergency preparedness and greater transparency around inspection regimes can reduce risks, but the financial reality remains clear. Without a massive funding boost, water managers are simply managing the speed of the system's decay. The vulnerabilities buried beneath New York are mirrored in nearly every major municipal water system across the United States. The challenge is representative of a nationwide struggle to maintain the unseen systems that sustain modern life. Across the country, the American Water Works Association estimates that replacing aging drinking water infrastructure will require an investment of $1 trillion over the next 25 years. This massive financial backlog has direct consequences for public health. Nationally, an estimated 400,000 miles of lead pipes remain in active service, carrying water to millions of households. While public attention occasionally focuses on high-profile disasters like the crisis in Flint, Michigan, those events represent highly visible symptoms of a large-scale national problem that quietly unfolds beneath the streets of hundreds of cities. According to the Environmental Protection Agency, An estimated 240,000 water main breaks occur every year across the United States. That is roughly one rupture every 2 minutes, bleeding clean water and undermining roads. Each break is a direct consequence of relying on pipelines that have long outlived their design lives. Many of these buried networks were installed during the post-World War era, designed for a population size and demand level that have long since been exceeded. As municipalities continue to defer maintenance, the gap between public dependence and system integrity expands. The ultimate test is whether action comes before somewhere becomes everywhere. To follow more investigative reporting on the critical systems shaping our world, subscribe to the channel. Today, the concrete beneath our feet is quietly reaching its limit. This is no longer just New York's silent gamble, but a blueprint for a fracturing nation. The question is not whether failure happens somewhere, but whether action comes before somewhere becomes everywhere. Subscribe for more in-depth investigative stories.